Good afternoon, Professor.
Hi, hello everybody. Good
Uh,
afternoon.
Hi.
So today we are going to discuss using graphs to represent and describe motion. And I've got some students asking that there's some question regarding the graphs on the homework, and we haven't talked about it, but don't worry, we're going to talk about it today, and we're also going to continue to solve some problems on Thursday. So without further ado, let's look at how are we using a different kind of representation to describe motion.
Professor, I had a question before class started.
Yeah.
So on Flip It Physics, I recall you like saying how like for the first week you're not gonna grade anything.
Right.
Or I don't know if that's true or not, but I completed like the first section, but like I completed it late, if that makes sense. Like I haven't finished the homework yet. I'm still working on the homework. But, like for the pre-lecture and the checkpoint, like it doesn't like show like I answer all the questions correctly, but it doesn't show that it's green. Like it's still like burgundy or red.
Send a screenshot of that to me. I don't think that's a problem. It could be just a delayed response. But if you have done it, that must be registered in the system. But if you're worried, send a screenshot of your scene to me and I'll take a look. And you're right, the first week of pre-lectures are not counted into the grades so that people have time to get it set up. Okay.
Oh, okay, got it. So like the whole section 1D, the kinematics, it's not gonna be in our grade book. Like section 2 will be though.
Just first week, which is whatever was due last Thursday. If I continue to get a lot of students saying they just get added to the class this week, then I might consider dropping 2 weeks of entire pre-lecture because some might need more time. But for now, I seems to be just dropping the first week, which was last Thursday. The pre-lecture on last Thursday seems to be have given enough time to everybody.
Okay,
does that make sense?
Yeah, no worries. That's fine then. I don't really have to worry about it because I did it, but I just did it late. But it's not gonna be in the grade book, so I'm fine.
Right. Don't worry about it.
Thank you, Professor.
Okay. Yes,
sorry,
another question?
Yeah, I have a dilemma too. So I tried logging into my the Flipits and it won't let me. So I tried using the forget password and that doesn't work either. So I tried creating a new account, but it said that I already registered. So I guess could you delete my account later so I can rejoin with a different account?
I see. Okay. Shoot me an email. We will work that out offline. Okay.
Okay.
I had the same problem with the password reset issue. You just have to call them and then they can figure it out.
Oh, okay. Thanks.
Okay. If it doesn't get resolved, shoot me an email. I'll work with you on that. Okay. The pre-lectures, no, you cannot do it late. You have to do it at the due time. But the homeworks, I have created 2 deadlines for each of the homework. Okay. So you can always continue to do the homework the week after it's due. Drop the lowest homework. The first homework is due this Friday. I usually have the policy to drop the lowest homework or maybe 2. I couldn't remember exactly when I put in the syllabus, but usually I always drop either 1 or 2 lowest homework. I'm getting a lot of questions on the text right here. When we read the text, we spend a lot of time on it by taking notes or simply read through it. Do it whichever you think is best for your studying habits. I think taking notes is good. But sometimes if you just want to get a quick read through, then just quickly read through it. But I would recommend taking notes at the same time. Okay, so let's describe motion. One way of describing motion that we all know how to do is simply just draw the position of a person at different times. So imagine I was talking about me walking across the room and you're recording my position at different instants, 1 second, 2 seconds, 3 seconds, and 4 seconds. And you can also plot all of this on the graph. So at 1 second, I'm at 1.1 meters. At 2 seconds, you measured that I'm at 2.2 meters. And at 3 seconds, and I'm at 3.3 meters, and so on, so on. By connecting these dots, you realize the position versus time graph looks like a straight line. So that is telling me something. Their information can be read from this graph. Is that I have moved equal distance at equal time interval, that showing that I'm walking through the space in a steady with a steady speed, right? In a constant velocity. So from a position versus time graph, you can read information from that is the velocity. By doing that, you simply take the slope of the graph. For in math, we all know to get the slope, you need the rise over run. So from here, you can take any 2 points on the graph, any 2 points. So for example, here and here, and from here to here, the change in the x direction is the y, or is the rise delta x. The change in the horizontal direction is the overall time, rise over run, that's delta t. So delta x over delta t give you the slope. And you can see that it's a steady slope all across the line, which means imagine if you're walking on this, if this is a ramp, you're walking on it, or if this is a hill that you're walking on it, you are experiencing same kind of steepness all the way through. It's not getting steeper or less steep at different locations. So always the same kind of slope. So that is a constant velocity because the slope is a constant in this case. So you can say your average velocity is, you do delta x over delta t, in this case happen to be 1.1 meters per second, or you can say this constant velocity, so that is your velocity at any instant. You can say my instantaneous velocity is also 1.1 meters at any given moment. It's the same velocity throughout. So that is, okay, from position versus time graph, you take the slope and you can get the velocity. The same holds true if you're dealing with a curve instead of a straight line. So this is a question on your pre-lecture. You have seen this already. If we were giving a graph of x versus t, this looks like a parabola, and you're trying to interpret how the velocity change over time from a position graph. So this is x, which indicate your position. We simply can just draw the slope at different places and see how it goes. So it's telling me the velocity at at t equals 0, whether that's greater or smaller at t equals 0, t equals 1, or 3, or 4. So you can see that at t equals 0, I'm right here. And to draw a tangential line, I need a slope that looks like this, right? That is my slope. So, and everywhere for the first half of the graph, so the left half of the graph, you can notice that the slope is always negative. You have a negative slope. And the right-hand side of the curve, you have a positive slope. So if you have a negative slope, that indicates you have a negative velocity, and if you have a positive slope, that means you have a positive velocity, right? And then how steep the slope is telling you the magnitude of velocity, telling you how fast that the object is moving. So the velocity at 3 and 4 are positive, and you can see that 3 is less steep than 4. 4 is much more steep. The slope is much bigger here. Here you have a bigger slope than 3. Here you have a smaller slope, right? So the correct answer is D. The velocity is greater than 0 at t equals 3 and t equals 4, which is larger than 0. Further, you can indicate that velocity at point 4 is even bigger than the velocity at point 3. So I have a question for you. Can anybody tell us, from t equals 0 to t equals 2, how does would you say the object is speeding up or slowing down? What would you say from t equals 0 to t equals 2? Between 0 and 2 seconds, would you say the object is speeding up or slowing down? Anybody would like to tell us?
It'd be speeding up.
Okay, so how can we tell that? So when I say speeding up or slowing down, I'm asking about the magnitude of your velocity. I don't really care about whether it's positive or negative.
It is slowing down.
Okay, so how do we know that?
The magnitude of the velocity is decreasing.
Okay, by looking at the slope here is very steep. Here is a little less, and you can see at point 2, I want to draw a tangential line. It will be a flat line. So you will indicate the speed here right at t equals 2 is how many? How much?
0.
Is zero. It's a zero slope. So yes, I am actually, the object is slowing down without here, because I'm asking about magnitude, you're saying it's slowing down, but you can see that indeed, if you're talking about this being a negative velocity, obviously a negative number is smaller than the zero. But it's in terms of magnitude, it is actually decreasing. So yes, you can see the object is slowing down and then speeding up again in the opposite direction. So that is a motion we can infer just by looking at the graph. Here we have a question for you. I don't think this one required to go into the breakout room. So here I'm just presenting the question, you can vote on it. We have 3 different position time graphs representing 3 different objects. So can we rank the speeds of these objects from the lowest to highest? And again, be careful that I'm asking about the speed. I'm not really asking about the velocity. Okay, so I'm only caring about magnitude.
Professor, I can't tell. Is that a right angle where C crosses between A and B?
It's not quite a right angle. Not really from the graph. It is not.
Sorry, but is A and B parallel?
Yes, A and B is parallel. A is parallel to B. Okay, we have had 80% of the vote already came in. Just 10 more seconds to finish the voting. Okay, so any last minute vote before I close it? Okay, let's take a look. All right, so we have a majority of you voted for B, and then we're pretty much tied between C and D. And let's take a look. So we agree that A and B have the same speed. You are correct, because A and B have the same slope. So velocity A and B are the same. And we also see that A and B have positive velocities and C is a negative velocity, but that's okay. We're only caring about the speed. So we just want to look at A and B versus C. Which one is more steep? So what do you think? Which one is more steep?
C.
Imagine you're walking on C versus you're walking on A and B. Obviously, we don't know the exact slope or exact angle, but it is obvious from the graph C is much more steep. So C has a bigger velocity, even though that is a velocity in the opposite direction. So you're right, B is the correct answer. Very good. From the lowest to highest. So now let's look at velocity versus time graph. The same kind of graph we had before. I have position versus time, which is a straight line that indicate I have a constant velocity. You can represent the same information by simply just draw a velocity graph, period. You can just choose to describe that motion in whichever way you want. So if you were to draw a velocity versus time, no matter at what time, the velocity is always a constant 10 meters per second in this case. So it's going to be a straight horizontal line running across. It's a constant velocity. So you can say average velocity is 10 meters per second, but it's also your initial velocity, your initial or your final or anywhere instant in between, because it's constant, it does not change. Have a constant velocity. So simply just drawing a straight line across the horizontal direction. That's pretty simple. And if you were given the position time graph that is, sorry, the share, need to share that again. Seems like I bring it out of the picture now. Can you see my screen or is it gone?
No, it's just black.
It's
Or-
black. Yeah.
It's gone, right? Okay, so let me stop share and share it again, see if that works. I don't know why it's gone.
Yeah, nothing's showing up still.
That is weird. Okay, there you go. I'm sorry about that. I don't know why it went away. So you can see if you have a position time graph that's a curve, look, this looks like a parabolic graph right here. And my velocity graph, I can kind of figure out what it will look like. So the velocity from here, you can see here, it seems to have a zero velocity because of zero slope. But as you go on, the slope is getting more and more steep as you go on. So if I draw my velocity time graph, I probably get a velocity that is increasing over time. And it turned out if this is exactly a parabola, then my velocity would be a straight line. And I'll show you guys why later on when we do the kinematic equations. So if your velocity is a straight line, that is indicating that my velocity is increasing at a steady rate over time, my position. So if you were taking sort of a camera, take a quick picture after every second, you notice that this person or this object is moving with bigger and bigger distance in between the same time interval because they are moving faster and faster. And you connect the dots, you get a parabolic curve. But the slope of the parabolic curve is giving you the velocity at any instant. So this is a constant velocity, looks like a straight line running across. This is a non-constant linear velocity that is increasing. So here is, and again, it should be a really quick vote. If I have a train that's moving along and I'm giving the position versus time graph, okay, which is sort of being hidden. Let me draw the graph one more time. It looks like this. So this is my position versus time graph. I want to ask you, what can you say about the speed of the train? So I'll let you take a look at this and do a quick vote. Okay, any last minute vote? Let's go for 10 more seconds. All right, if there's no last minute vote, let's take a look at this together. I'm going to end the poll. It seems like we are pretty much tied between B and D. The that we think that at least it's slowing down for some of the time, if not all the time. So let's take a look at this. So this is my graph. If I could redraw this again, this is what it looks like. So maybe it's not so obvious just by looking at the graph. So it's always helpful to draw the tangential line. So here I have already added a few lines sort of at the beginning of the motion, this one, and in the middle, and then later on. So can we tell that these lines are continuing to get bigger or smaller, or is it increasing for some of the time and then decreasing for some other time? If it helps, you can always extend the line a little bit if that helps you to see. So looking at this line, imagine you're holding the incline and you kind of move it up or down, more steep or less steep. Would you say these three lines as time goes on is getting more flat or less flat? Is it getting closer to the ground, right? Level? Yeah, it's getting more flat. Another way is to say it's getting more flat and less steep. So yes, so which indicate the velocity or the speed is decreasing. So it is slowing down the whole time. It's slowing down the whole time for the train. Okay, and if you look at this is really just kind of flipped. It's the parabola kind of turned upside down, right? So earlier, if we say when it's going like this way, it's increasing, then of course here, if you flip it, it's always decreasing the whole time. So here is another question. It's a little bit more complicated, but since we have the background earlier, we should be able to do this. Here I'm showing a velocity times graph. And from the velocity, I want to get the displacement the other way around. So the velocity, you can see it run through two quadrants. You can see at the left-hand side of the time axis, the velocity is decreasing. Okay, decreasing becomes 0. And then the velocity is increasing, but in the opposite direction as time goes on. So that is how the velocity goes. Which one of these would you think best describe the displacement versus time? So it's sort of the other way around. I'll let you go into the breakout rooms for about a minute or two, and then when you come back, you can vote on this. So take a quick screenshot of the picture so you don't lose it. So you continue to be able to look at it when you go to the breakout rooms. Okay. So okay, there you go. Another 10 seconds for the voting. Okay, I'm going to end the voting and then we can share the results. Okay, so here are the results. Anybody would like to share their thoughts with us and tell us what method did they use to pick an answer for the velocity? Given the velocity, we want to find x versus t. Anybody would like to say a few things?
Integrating the velocity.
Yes, you integrate the velocity to get the x. And can you say more about that? So is that the method that you use to help you choose an answer?
Yeah, I just integrated and I saw it was like negatively sloped, so I chose A for the negative parabola.
So to integrate it, you mean you have to, first of all, find out what this function is. Do you write out the function for this particular line?
Yeah, it was, I just put it as like a negative x.
Ah, okay, so this looks like a negative x is a function and you integrated it to get the velocity. Very good, to get the position. And we will discuss that later on. And you just plug in x versus sort of an integral of x dt. Any other method? That's very good. Any other method?
I also looked at the graph, and then I saw in the velocity graph that at t equals 0, the velocity is 0.
Okay.
So the displacement has to have a critical point at t equals 0. So it's either A or B. And then
choosing a critical point. That's a very good technique in physics. Okay. And either A or B. Okay. Here, flat. Here, flat. And how do you choose between A and B?
And then because for negative t, the velocity is positive, therefore the tangent line has to have a positive slope for negative t in the displacement. So that's how I chose A over B.
Yes, very good. Here on the left-hand side, you can see these values are all positive values. They're above the axis of v larger than 0 axis. So you should have a positive slope as indicated on the A graph. Yes, so A is correct. That this is corresponding to a position graph. Very good, excellent. So you can see if you have two different graphs, one have a bigger slope than the other, and that indicating that one of the velocities is increasing at a higher rate than the other velocity. So again, so we have talked about two different graphs already. Position versus time, velocity versus time. The last graph is acceleration versus time. And the relationship between one another is very similar. It's sort of from position to velocity, you take derivative. From velocity to acceleration, you take the derivative again. And to reverse from acceleration to velocity, you integrate it. From velocity to position, you integrate it. So here, if you have the blue line here, this one is at a higher slope, bigger slope than the red one, indicating this one has a bigger acceleration. So these two are giving me a constant acceleration motion, meaning that something is accelerating at a steady rate. Here is 1 meters per second square. Here is pretty much 2 meters per second square. So one, let's say this is one car versus another. One of them is speeding up at a higher rate. There's some comment from you guys that to read the acceleration on a graph is difficult because sometimes it's negative, sometimes it's positive. And we were talking about how that doesn't really tell us it's speeding up or slowing down. So how do we connect whether something being positive or negative to something being speeding up or slowing down? So I want to show you some examples to address that comment. Let's look at these three graphs one by one. First of all, we're just going to focus on the first one. This one just showed me I have a velocity that is increasing. So something is speeding up in the positive direction. That simply means that maybe you have defined to the right to be a positive direction and your object is moving also to the right. So you're speeding up in that direction. And here the slope of this is a positive slope. You have an acceleration that is also larger than 0. So acceleration is also pointing to the right. So you are increasing your speed. On the other hand, you can draw a second graph here. You can see that velocity starts from 0. It is increasing in speed, but it's increasing your speed in the negative direction. So if I say to the right is my positive direction, here my object is moving to the right. Here my car is moving to the left, but it's also speeding up. My acceleration is a negative slope, is less than 0, because the slope is less than 0. This one, I'm first moving with a non-zero speed, but I'm slowing down. I'm decreasing my speed until I get to 0, and I continue to, you can say I continue to decrease my velocity, but it's increasing in speed in the reverse direction. So this looks more like your car is moving in this direction, but you have given an acceleration in the opposite direction, slow you down, so it comes to a stop, and then reverse direction to go back in the opposite direction. And again, acceleration in this case is less than 0 because it's always pointing to the left, which is the opposite direction to the positive direction that you have defined. Again, don't worry too much about, the sign of the accelerations. You have to look at whether the acceleration and velocity are in the same direction or not to tell if it is speeding up or slowing down. So that's something I wanted to emphasize. So here is a checkpoint question you have already done. I wanted just to go through it relatively quickly in class. Here I have a position versus displacement versus time graph. And this is a velocity versus time graph. So from these two graphs, we want to choose the acceleration versus time graph. The correct answer is A. I know you did it already, so you probably already know the correct answer. There are some possible reasons people might give to choose A or B. So now we have already done this. Let's take a look at this together. So since we are looking at the acceleration graph, it's probably easier to work from the velocity time right away because that is given, because we just want a slope on the velocity versus time graph to give us. So the first half, you can see that I'm getting a negative slope, so I should have a negative acceleration. And this slope is getting less and less steep, right? Because it's becoming more and more flat. Here you have a 0 slope. So I should have a negative acceleration, negative, and it's decreasing because the slope is getting more and more flat until it goes to 0. And you have a positive slope and getting more and more steep, and it's increasing. So the correct answer is A in this case. So here we have talked about these 3 different kind of graphs and how you can read one and then find information about the other simply by looking at the slopes. And some of you have also used it, worked it out in a mathematical way, which is very good. You can assume a function and you integrate it to get the other. So next I want to talk about kinematic equations because there are some comments from the pre-lecture. There are a lot of variations of kinematic equations. I agree with you. So my hope is I will give you a universal equation so that you can organize your equation around the most basic equations and don't have to memorize a lot of them. It's really just come down to 2 equations, the 2 fundamental equations, which is not something you even need to memorize. It's something we understand. If we understand this, we don't have to memorize it. We can just write it out. All the equations you see in pre-lecture or in your book come from these 2 equations. These are fundamental. These are the definitions of velocity and time. The definition of velocity, that it is a change of position over time, the derivative of x over time. So that is a definition. the acceleration is the change of velocity over time, the rate of change in velocity, so dv over dt. With these two equations, you can derive any kind of kinematics equation that you want. Here, I want to demonstrate the derivation for starting from the first one. And I have my lecture notes, and you can look at my derivation for the other one. So let's start with the first equation. That I'm going to start with this fundamental equation that v is dx over dt. And I'm going to I'm sorry, actually, I'm going to work on this one, not this one. I missed it. I'm going to start with a equals dv over dt. And I'm working with a constant acceleration type of motion. So here, I will integrate both sides of the equation. So I'm getting velocity as a function of time, and I'm dealing with a constant acceleration. So if this is constant, I can take it out of the integral. So this is a very simple integration. So you have a times time, and there's probably some constant, because going from here to here, you take the derivative with respect to time, the constant always drops, right? So when you do the integration, you always have a constant. To define this constant, we just need to figure out what the initial condition is. Initially at t equals 0, at the beginning of the motion, you have some kind of velocity. So we usually call it v at t equals 0 is some constant. Let's say v naught, v0. So we also call it v naught. The beginning of the so at the beginning you have some kind of velocity, which is usually given your initial condition, and you can plug that in to get this constant. So plug it into here. So a times t equals 0 plus constant should give you the initial velocity v0, and this is 0. So my constant should simply be v naught. And here I get my function v as a function of time is a times acceleration times time plus initial velocity. So that is the equation you have already seen, right? This is the equation for a constant acceleration. Your velocity is increasing over time in this way. You can do the same thing with the other equation, but I'm not going to do it in class just to save time. So you can integrate. You can plug your v here as a function in here, and you integrate, you get acceleration. You get the x function. So I'm going to give you the results. So x versus t as a function of time is your initial position plus v naught t plus 1/2 acceleration times time squared. This is the other equation you have already seen. So I wouldn't say that every time when you do homework or at an exam, you always go back to these two equations and you start the derivation process all over again. That's not what I mean. But I'm saying, even if you forgot, if you understand how these equations are derived, the worst case scenario, you can always derive it one more time. But obviously, we have already derived it. I hope that now you have a problem, you simply just go ahead and just use it that way. But I want you to know that where it comes from. It's come from the definition. So these two are the equations we pretty much all you need to know for a one-dimensional kinematics for a constant acceleration. So velocity at any given time is your initial velocity plus the increase. How much you have increased is your acceleration times time. Your position is also your initial position plus your initial velocity times time plus 1/2 acceleration times time. So you can see this is a parabolic curve, parabolic function, and this is a linear a line. Sometimes we derive an alternative equation is here. it is not a independent equation, because if you combine this one and this one together, you can get the third one. You can derive the third one. But again, I'm not saying you should always derive it when you have an exam. You are already given one. You just go ahead and use it. But you should know that where it's coming from. Again, it's coming from these two combined, and you can always derive it. Now, the choice of the equations, I think one of the difficulties students encounter is we were given so many equations. I don't know which one to use. It depends what the quantity that is already given. Making an observation that in these two equations, you have some information about the time, right? But in this case, you don't have anything about the time. So if there's a problem that tell you, for example, velocity, tell you acceleration, tell you something about position, and didn't tell you anything about time, you probably would think, okay, maybe this one is a bit easier. But in the other case, if you're given something about the time, perhaps using the other equations are easier. So I may be over dramatic saying there are only two equations you need to know. These two are the fundamentals definition, but it really just boils down to these two equations that you get used a lot. And we will practice it today by using these equations to solve problems. There is a variation or simplification when you have a constant velocity. Again, I don't recommend you to memorize to yourself, okay, what is the equation again for constant velocity? Don't memorize it, but instead try to understand the meaning of the equation. That is much more efficient. So you can see that constant acceleration is a special case of constant velocity is a special case of constant acceleration. It is when your acceleration is equal to 0, right? Because there's no acceleration. You're not accelerating. Your velocity remains constant, does not change. But the equation you derived also applies. It's simply saying I have a constant acceleration. In this case, my constant is a 0 constant. So you can see these two equations you just derived, you simply simplify it by plugging acceleration equals 0. You apply a equals 0. So velocity becomes velocity equals v naught. You are remaining this constant velocity to begin with and never change. Constant velocity, right? You don't even need to memorize it really. And here again, you don't have to memorize. You can plug it in 0, and then you can say my position is my initial position plus velocity times time. Now, these two I don't think you need to memorize, because if I'm telling you, okay, beginning you're at 50 miles away from your house. Let's just pretend you're driving in a straight line. You're initially here, 50 miles, and you're driving with a constant velocity of another 5 miles per hour for 2 hours, right? You calculate where you end up. So it's just going to be 50 times 2 miles. You end up with 150 miles away from the house. So something that like that, it's something you already know. It's not even new physics. So that's what I'm saying is don't try to always thinking there's something you need to memorize, and that can help you eliminate some mistakes. Okay, so here before I go on, I do have a series of 3 or 4 quicker questions that's all about one particular problem, but I'm going to break it down into 4 quicker questions, do it one at a time. So before we can go ahead and solve our problems together, are there any questions about the kinematics equations, about the derivation process that I just went through before I go on? Okay, if there are no equations, let's take a look at this problem. We have a truck traveling 50 kilometers per hour, and that's, if we want to change everything to the standard units, that's about 14 meters per second. It's already converted for you. Approaching a car stopped at a red light. Now the truck is 100 meters away from the car. and the light turns green, the car immediately begins to accelerate to a final speed of 100 kilometers per hour. So this is the fastest the car could go. Right? Once the car reaches that speed, the car is going to maintain that constant speed for the rest of the trip. So which of the graph represents this situation? I want to let you know that without doing more calculations, hard to narrow it down to just one graph, but I'm just throwing out there as sort of something to begin our thinking process. So I'll give you 2 minutes to read the problem. And also at the same time, I want to show you how to solve a physics problem. I want to model the process for you. It's always good to draw a picture, to visualize the process. Try to draw the picture on a piece of paper on your notes by yourself. And you can also think about this particular question. But I want to let you know you probably cannot narrow it down to just one particular choice. Okay, so I'll give you 2 minutes. Okay. Someone said my audio is a little harder to hear. I put in I don't know if I increased my speaker. I don't know if that worked. Let me know if you have trouble hearing me. So I'm going to assign breakout rooms for you to, you can draw the picture together, have a discussion, and sort of just visualize the process, okay? Okay, all right, 1 second. And take a screenshot before you leave the main session. Okay, we all came back. So I wanted to, as you finish the voting, you can still put in your poll as I draw the picture. I want to model how we solve a physics problem. It's nothing like, it's simply by, if you're reading the story, right, you probably are formulating a mental picture in your head. And physics is really just translating that on a piece of paper. So let's draw this picture. Here we have a car that's parked at a traffic light. So this is your location of your car. And a truck is behind the car, is at 100 meters behind the car right now. So we'll draw a picture and at the same time we label the quantities that is given. And you have the truck right now. At this time, the truck is moving, and let's label the quantity that's given. We are giving the velocity of the truck, which is about 14 meters per second, moving to the right. And the car right now is stopped. So that is some information about the car. So initial velocity of the car is 0, that is given. We're also given the acceleration of the car, which is 2 meters per second squared. That's the information given in your problem statement. And we know that the maximum velocity the car can go is 100 kilometers per hour, which is double the 50. So it's 28 meters per second. So that is given. You see, that is it. That is all the information that the problem is giving me. And I translated the mental picture onto my piece of paper. So first step in solving a physics problem, I encourage you to draw a picture that including label your quantities. Okay. This question can be answered, or at least we can narrow it down by already finished drawing the picture. So let's look at this, your results. I'm going to, have I got all the polls coming in? I'll give you 5 seconds to put in your last minute vote, and then we can look at the results. Okay, I'm going to close it now. So a lot of you voted for B and C. Then D gets some votes as well, and there's some A's. So yes, I would say B looks very close to the description that was given. Let's look at what story B is telling us. Telling us that the truck here is behind the car, okay? They're not at the same position to begin with, indeed. Now, if I have defined, I should probably define a coordinate system, and I might as well define the x equals 0 to be where the car is. You don't have to. You can put where the truck is. That's totally fine as well. But if you put it where the car is and define this is the positive x direction, right? Which means your car is parked at the origin at the time of the beginning of the process. Your truck is behind here at 100 meters, right? Behind the car. And your car is accelerating. So your line should be a parabola. There's a curve, but your truck is traveling with a constant speed. So B looks very similar. Some of you choose truck, so choose C, right? The difference between B and C, there are 2 differences. One of them is the location of the time equals 0 part. And I can say that this one is not correct because the truck and the car at t equals 0, they're not at the same location, right? The truck here is here, the car is here. So they should not cross. So not C. Another thing that difference that C and B is whether the truck and car will meet at some point. And that's all the difference between B and D. D can also be correct though, right? Because the truck is behind the car right now, and you also have a curve and a straight line, and then they may meet at some point. So B or D can be correct. We don't really know which one is correct if we don't do further calculation. It might be B or might be D. So B says the truck is never going to catch up with the car. D says the truck can catch up with the car at some point. So which one is it? Okay, let's figure it out. So the next question is, how long does it take for the car to reach its maximum speed? Now, the reason I ask this is I want to figure out, okay, because the motion of the car is different. I need to analyze it in different ways. First, when the car is doing constant acceleration motion, and after that, it's doing constant velocity motion. So I want to be able to tell exactly when I need to consider the car for a different kind of motion. So the first question is, how long does it take for the car to reach its maximum speed? I will let you, you can simply work on your notes right here. I'll let you vote on this here, right here. And as you vote, again, I'm going to go back to my previous page and continue with my solution here. So the question one I'm trying to answer is, how long does it take for the car to reach the maximum speed? Okay, so here you have draw the picture. That's your first step in solving the problem. The second step is you pick the relevant physics. Decide what kind of physics is involved. I wouldn't call it simply choose equations, because that you choose equation because you know what the physics is about. It's not randomly just plugging and chugging. You choose it because you really know why. So in this case, the physics involved is the motion of the car. So to pick out the physics that is relevant, I want to ask you, what kind of motion do you need to consider for the car? What kind of motion is a car? It can be described. Today we have talked about constant velocity. We have talked about constant acceleration. So which one of these can be used to describe the motion of the car? What do you think?
Constant acceleration.
Constant acceleration. Okay, so constant acceleration, we use the equations that we derived. We have two equations. We have another equation. So which one might be relevant to answer this question? This one or this one? First one or second one?
Which one?
First one.
The first one, right? Yes. Okay, so how do we know which equations to use? To look at which one was given. I know V naught is 0. I know A is 2. And I know V max is 28. Okay, so let's look at your voting results. I'll give you guys a little bit of time to finish your voting. Seems like I have 30% of the people have voted. So I'm going to go back to my question so you can take a look at the question again. The question is, oops, sorry. How long does it take for the car to reach its maximum speed? Okay, 70% have voted. I'll give you 15 more seconds to finish your vote. Okay, any last minute vote before I turn it off? Okay, I'll end this. So here are the results. B got the majority of the vote, and very good, that is correct. Excellent. So we are pretty much kind of done with our calculation here. We just need to plug it in, right? So the car begins with this velocity and it ends with the terminal velocity, which is 28. It cannot go any higher than that. So plug it in and you will get the time, the total time it takes is 14 seconds. So the answer to this question is 14 seconds. Okay, so you might wonder, okay, now we know it takes 14 seconds. We still couldn't answer the question whether the truck catch up with the car or not. So let's further ask one more question. Okay, so whether the truck catch up with the car, you want to see how far the car travels and how far the truck travels to see if they ever meet. So during this time, during these 14 seconds, how far did the car travel? Okay. And I will let you vote on this again. And as I let you vote, I'm going to continue to solve my problem, okay? To solve this problem. If you know your answer, feel free to put it in, or if you want to wait as I solve it along, and then you can do that as well. So during this time, how far did the car travel? That's the second question. Question 2 is right here. And again, I want to choose the physics. The same kind of physics applies. So the physics of this problem is still being a constant acceleration type of motion. Once I decide on the physics, I can figure out the relevant mathematical relationships. Now I want to know how far it travels. It's asking me about the position. So that's why I'm going to use my second equation. This is what so first we decide the physics, and then we decide the equations that is applicable to the physics. How far it travels, we just want to know the x, which is because you are starting at 0 and then you're ending up at some other distance away. So what is x? X equals v naught t. V naught is also 0. Is really just 1/2 at squared. I'm going to plug in acceleration is 2 meters per second squared, and time is, you have calculated, is 14 seconds, 14 squared. We will be able to get our answer, right? So given the vote I have right now, is I have a majority of choosing for C. So we don't have to finish the voting. I will just let you know the results right here. We have majority 86% choosing C. So, okay, let's see. It's 1/2 times this cancels, you just have 14. The units become meters, right? The seconds and the seconds cancels, is just 14 squared is going to be 196 meters. So yes, C is correct. So you can see I'm slowly getting closer to the answer to my first question, is whether the truck ever catch up with the car. I still don't know the answer. But once we answer this question, we will be able to figure it out. During this time, how far does the truck travel? So I want to go back because I want to draw a new sort of a graph to help us understand the whole situation. Let me go back here. So this is the position, time. The car starts at 0, x equals 0, and it is moving with a constant acceleration, so it's something like that in terms of the curve. And at this point, 14 seconds, the car has traveled 196 meters. That's what we calculated. Okay. The truck, on the other hand, at the beginning is 100 meters away from the car. And the truck travels with a constant velocity. So it's going to be a straight line. I don't know if they will meet somewhere around here. I don't know. So you can see that in order to finish the line of the truck, I want to see, okay, during the process of 14 seconds, how far did the truck travel? And my question, next question, question 4 is, how far did the truck travel during the 14 seconds? Right? Again, pick out the physics. So what kind of physics can describe the motion of the truck? What kind of motion is the truck? Anybody?
Constant velocity.
Constant velocity, very good. The constant kind of motion for the truck is constant velocity. Now, knowing that, you know which equations to use. So how far is asking position. So I need a position equation. So position of the truck is the initial position of the truck plus velocity of the truck times time. Okay, so that is, you remember that is the equation we have showed you, I have showed you previously. Okay, so there are two ways you can do this. You can either say, okay, how far is simply asking how far it went. So the total distance it traveled is x final. So here sometimes I need a different, I need to be a little bit creative with my symbol just to accommodate all the different things here. All right, so here I might do subscripts final and initial. Final, initial of the truck. So this is really asking me, what is the final minus the initial, right? So how far I traveled. You can do that, or you can say, I'm just gonna calculate my final position. You can do that as well. So if you're doing the final position, that is the initial position, is at negative 100, right? So plug in one negative 100 meters. And the truck travels with 14 meters per second, and give it 14 seconds. So you get negative 100 meters plus 196 meters. And the truck ends up at a position of 96 meters. So when the car is here at 14 seconds, the truck is at 96 meters. So somewhere here. Maybe a little higher. 96 meters. So this is where the truck is. So I'm going to continue to draw my line. Show this is my truck. Okay, right here. So okay, this at this time, the car is here, the truck is here. After this time, the truck will continue to be the straight line, and the car will become a straight line. The car cannot speed out anymore. So the line for the car becomes a straight line here. The car will travel with a constant velocity after 14 seconds, and the truck continue with this velocity. And take a look at how far the truck is behind the car right now. So at 14 seconds, the truck is still 100 meters away from the truck, from the car. The truck have managed to, decrease their distance in between, but they can never catch up with the car because the car now reached the maximum speed, which is twice as fast as the truck. Is only gonna get faster. It's only gonna get further away. And here yet the truck is still behind the car with 100 meters. You can see further on, these two lines will never cross. So when we went back to this equation, to this question is, B is indeed correct because they can never, the truck can never pass the car or meet the car. So B is correct. If I were to change the problem a little bit, I'm going to change my acceleration for the car to be much less, than giving the truck a chance to catch up. So I won't have time to solve it, but I'll show you sort of the rough process. So if I had changed the question to be, the car accelerate at 0.5 meters per second, much smaller acceleration. Now you do have a chance to catch up with your with the car. So here's how you're going to solve it. You are going to, so you want the car and the truck to be able to meet, right? Then you make these two equations to be equal. The final position of the truck is equal to the final position of the car. That means they meet, they pass each other. They're at the same location. And you make this equation equal to that equation. So you end up having solving the time here. They may not all be valid because you have to think about, okay, within this time, am my car all accelerating? If it's not, you have to break down the process into two steps where the car is accelerating and then where the car is a constant velocity. And you also need to think about maybe they will even meet twice. One catch up with another, and then the another catch up with the other one first. The second solution is when the car finally passes the truck. But first, the truck will pass the car at 8.5 seconds. And the car will pass the truck at 47.5 seconds. So that all comes from your mathematical solution. So if I were to draw the graph for this one, it might be more like this, where the truck passed the car here. And the car will pass the truck here. And then, of course, after that, they will never meet. So this is simply the same problem. I'd simply change my acceleration and you have a different result. So today we have talked about these kinematic equations. Simply, there are only two, right? One for velocity, one for position, and there is an alternative one, which can be derived from the first two. And you have a constant velocity. This equation, I would say you don't even have to memorize. We already know how to do it just with our daily experience. Or if you want, you can always treat this as a special situation, special case where acceleration is 0 for the previous one, and you can get this equation as well. So that's all we're going to talk about today. And we will continue to solve more problems and even adding motions in two different directions, not just one direction on Thursday. Okay, I have office hours coming up next 2 days. If you want to ask questions about homework, you're welcome to come and ask me there. Okay. Okay, see you guys on Thursday if I don't see you at office hours.
Thank you.
Professor, have a good day.
Thank you.
Thanks,
Bye, Professor. Have a good one.
Thank you, Professor. Have a great day.
Bye. Bye, everybody.
Thank you.
Professor, I have a question.
Yes, go ahead.
How did you derive that v squared minus v0 squared equation?
Okay, so we can see these two combined to get this one. I want to eliminate time. So from here, are you still seeing my screen?
No, I don't see your screen.
One second, let me bring it up. Can you see it now?
Yeah, I can see it now.
Okay, so I want to get rid of the t. So I'm going to represent t using the other variables, this v minus v naught over a. And I plug that into the second equation. So whenever you have t, you replace it with this. And whenever you have t, you replace it with this one. And you simplify it. So from the first equation, delta t can be represented using v minus v naught over a, right?
Right.
Yes. And because here, this equation does not have t, so you want to get rid of the t. Whenever you have delta t, you replace it with the other quantity. So here you have delta t. You replace this delta t with what I just have here, okay? And plug it in here as well, this delta t. So you got this, you simplify, and then you will get this equation.
All right, I think I got it. Thank you, Professor.
Okay, no problem. Bye.
Professor, I have a question.
Go ahead.
So for the homework, I know we have to read sections out of the book, but when I was reading, I read all of it, and my progress bar hasn't moved. So I was wondering, like, if it's supposed to move or
Lecture, right?
I'm sorry.
Do you mean the pre-lecture?
No, the OpenStax
No,
chapter.
you don't actually track your reading for the OpenStack. I could not track your reading. The reading is not assigned. Is not your homework. The reading simply is just a place for me to link you to the relevant reading. You can read it anytime you want, or if you don't have time, some week you don't read it at all, I have no way to track it.
Oh, okay. I was just making sure because I thought like
Yeah,
I was
I know it can be confusing. It's showing up as a tab in the calendar, but it's not a task.
okay. So I don't need to worry about it.
Yeah, don't worry about it. But good reading is always good, so keep up with the good work.
Okay.
Okay, bye.
Thank you, Professor.
No problem.